Just a few short years ago, we were absolutely mesmerized by basic chatbots that could, well, write a decent email. But man, the landscape has shifted so dramatically since then. We're now looking at systems that can essentially run entire companies entirely on their own. Welcome to this explainer. Today, we're going to unpack the cutting-edge architecture of 2026 AI systems. But instead of just
Mhm.
vaguely talking about what AI can do, we're going to build a modern, working AI system from the ground up. By the end of this, you'll understand exactly how the world's most advanced systems think, retrieve information, and most importantly, how they remember.
Okay, so here is our roadmap for today. 1. The 2026 frontier models. 2. Rise of reasoning models. 3. RAG, chunking the elephant. 4. Advanced retrieval and graphs. And 5. LLMs as operating systems. Let's dive right in. We're starting at the absolute top of the tech stack with the raw computing engines. Section 1. The 2026 frontier models.
To really understand where we are in 2026, we have to precisely define the caliber of technology we're working with here. A frontier model isn't just some incremental upgrade or a slightly faster text generator. No, it's an elite system that exhibits expert-level reasoning, incredibly broad knowledge, and a massive computational scale. These are the engines pushing the absolute boundaries of science and dominating industry-standard tests. The big takeaway here? We are way past algorithms that just guess the next word. We're dealing with synthesized subject matter experts.
And what's really fascinating about the current landscape is the total death of the one-size-fits-all AI. I mean, you wouldn't hire a brilliant mathematician to write a marketing novel, right? In 2026, you don't use the same model for every task either. The top models right now each absolutely dominate a highly valuable specific niche. You've got GPT-5.5, effortlessly crushing complex math. Claude Opus 4.7 is the undisputed champion of writing and agentic workflows, meaning it's the best at using external digital tools. Meanwhile, Google's Gemini 3.1 Pro takes the crown for long context windows, processing 1 million tokens of information at a time. Grok 4 leans heavily into coding with real-time web awareness. And then there's DeepSeek V4 Pro, which literally disrupted the whole market by offering frontier-level performance in an open-weight, self-hostable package.
To put that disruption into perspective, when an open-weight model like DeepSeek V4 Pro hits nearly 83% on complex real-world coding benchmarks, it proves something massive. It means open-weight models are actively rivaling the proprietary corporate giants. Enterprise-grade AI is no longer locked behind a restrictive paywall or some massive subscription fee. It's accessible to independent developers and businesses everywhere. So the raw brainpower of our AI system is not only more powerful than ever before, but it's universally available. But, raw static compute just isn't enough anymore for the complex problems we're trying to solve. And that brings us to Section 2, Rise of Reasoning Models. This is a fundamental transition in how artificial intelligence actually operates. Traditional LLMs were essentially highly advanced autocomplete. They just spit out a static, one-shot generation based on their training. It's kind of like someone blurting out the very first answer that pops into their head. Reasoning models, or RLMs, do something incredibly different using what's called test-time compute. Think of it like someone grabbing a piece of scratch paper, actively working out the math, crossing out their mistakes, verifying their own logic, and only then handing you the final verified answer. Through reinforcement learning algorithms like GRPO, they actually learn to internally debate a problem before they even speak. But, as you might guess, this amazing internal processing creates a major bottleneck for tasks where speed is critical. If a model generates a massive, complex chain of thought for every single query, we've got a problem. You absolutely do not want a supercomputer burning $1's worth of electricity and taking 30 seconds just to answer, "What's the weather like today?" So how do these reasoning models avoid overthinking the simple stuff? Well, the industry solution relies on calibrating the effort. Developers can now explicitly map the AI's brainpower directly to the problem at hand using tools like Google's thinking budget or dynamic reasoning toggles. This is a massive game changer because it saves latency and, of course, saves money. Need a quick high-level summary of an email? Turn the reasoning way down. Need to solve a 20-step logic puzzle for a massive financial audit? Crank that thinking budget all the way up and let the model chew on it. You get the exact level of intelligence you need, right when you need it. Now, even the smartest brain needs good, accurate data to reason with. This brings us to Section 3, RAG, chunking the elephant.
I absolutely love this analogy because it perfectly highlights the problem of retrieval noise. If you shove a dense 200-page legal contract or a giant corporate knowledge base into an AI all at once, it just gets totally overwhelmed. It starts hallucinating facts, it loses track of crucial details buried in the middle of the text. The document is simply too large. You cannot eat the elephant in one bite, right? It has to be divided.
But here's the catch. If you just cut that elephant up randomly, you completely destroy its underlying meaning. Sentences lose context, and the relationships between ideas just vanish. Good chunking isn't just about making text smaller, it's entirely about preserving meaning. You have to turn your documents into perfect, semantic Lego pieces. Each chunk has to be modular, meaningful, and composable. When you do this right, the AI can effortlessly snap together only the specific, relevant facts it needs to build your answer, leaving all the rest of the noise behind. This creates a beautifully efficient 4-stage pipeline. First, your raw document is cleanly chunked and embedded into a database. Then, when a question comes in, the AI searches for the exact right Lego blocks, retrieves them, and augments its own baseline knowledge to give you a perfect, cited answer. The ultimate takeaway here? The absolute intelligence and accuracy of your AI at the end is entirely bounded by how well you chunked your data at the start. Better initial chunks always equal better final answers. But what happens when questions get highly complex and simple keyword matching just isn't enough? Let's explore Section 4, Advanced Retrieval and Graphs. So standard RAG is a static, linear search. You ask, it searches, it answers. Agentic RAG breaks that linearity completely. It empowers the LLM to act as an autonomous agent that actively decides when to retrieve information. It evaluates the results it gets back, and if those results aren't good enough, it actually rewrites its own query to self-correct. Imagine asking an AI to research a corporate competitor. Instead of just handing you the first PDF it finds, Agentic RAG lets the model act like a junior analyst. It pulls a document, reads it, realizes it needs a financial statement to verify a claim, searches again for that specific statement, and double-checks its own sources before ever giving you the final report. Meanwhile, GraphRag approaches the problem from a completely different, almost three-dimensional angle. It extracts entities and relationships into a structured knowledge graph. This allows the AI to perform what we call multi-hop reasoning. Think of it like a detective connecting strings on a corkboard. GraphRag allows the AI to connect a suspect mentioned in document A directly to a mysterious bank account mentioned in document B. It's not just finding keywords anymore, it's actively connecting the dots across your entire dataset to answer broad, complex questions. All right, so we have the reasoning brain, and we have dynamic data retrieval. To bridge the gap to true autonomy, we arrive at Section 5, LLMs as operating systems. You see, without memory, an LLM is essentially like a brilliantly smart colleague who tragically gets amnesia every single time you close the chat window. They are completely stateless. To fix this, researchers created the LLM operating system. Just like your physical computer's OS manages RAM and a hard drive, the LLM OS actively shuttles data back and forth. It pulls from an unlimited virtual context, basically the massive hard drive of all past conversations, and slots it perfectly into the limited physical context window of the LLM, right exactly when it needs it. Giving an AI this persistent, self-editing memory completely changes the game. It solves the stateless problem and means the agent actually learns your specific preferences and workflows over time. It can pause a massive, complex coding project on a Tuesday and remember exactly where it left off when you ask it to resume on Thursday, constantly updating its own internal hard drive. Through tool calling, it writes to its own memory, achieving genuine, continuous learning without ever needing to be fundamentally retrained by engineers. Which leads us to a pretty provocative final thought. We've just built a system featuring expert-level reasoning brains, dynamic multi-hop data retrieval, and persistent self-updating memory. As these autonomous reasoning agents become our new operating systems, seamlessly handling complex digital workflows entirely on their own, are we actually witnessing the end of traditional software as we know it? It's a massive, absolute game changer in how we interact with computers, and one we will definitely be watching closely. Thanks for joining me on this explainer of the 2026 AI architecture.